So in today's class, we are going to take up a new chapter, that is conservation laws. We will talk about in this particular chapter. This is chapter 4th actually. So in this particular chapter, we'll go through the introduction of very basic introduction of conservation of laws. What are those? Next, we will take up the time derivatives of volume, and which is essential for deriving other equations. So this could be the fundamental of mathematics, you could say. And in that, one second. Okay, and in that we'll talk something about Leibniz theorem. Sorry. Leibniz integral theorem or rule. And based on this Leibniz principle, we are going to do the derivatives of particular volume, and which is essential part of our fluid mechanics to derive the conservation laws related to fluid mechanics. This could be advantageous for us. We'll talk about conservation of mass, which is nothing but the continuity equation. And in this particular course, in this particular chapter, we'll take up things in integral way rather than differential way. Integral form, okay, rather than differential form. And we'll discuss what these all about. So differential form of continuity we have already seen. That was, what was that? Dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So that was our continuity or mass conservation equation, and that was essentially a differential form. And there will be another way to look at those conservation equations, that is called integral form, and we'll see what are those. We'll also talk about the origin of forces in the fluid may occur, may constitute body force or surface force. And since we have already looked upon the surface forces, how because of those stresses, how the surface forces will come, and we'll also talk about the body forces in that context. Stress as at a point we are going to look upon. At certain point we will take up a elementary element, and we are going to see what are those stresses that will act on this particular point. This is infinitesimal point. Let's suppose this is 1 point P. We'll see the conservation of linear and angular momentums associated with this elementary particle, and which will be integrated over throughout the volume later. We'll also see the constitutive equations for Newtonian fluids. Constitutive equations means in some sense you can say it is the connection between kinematics and dynamics. Then we'll talk about the usual standard Navier-Stokes equation, that is viscous form. Viscous form of, obviously, conservation of, this is nothing but the conservation of linear momentum, but initially we'll talk inviscid form and then the viscous form, and that we call that viscous form of conservation of linear momentum as Navier-Stokes equation. We'll also look upon the Bernoulli's equation in integral way, not the usual way what we do, what we usually do. So the energy being constant, so half rho v1 square plus rho gh1 plus p by rho or something. yes, is equal to P1 P2 by rho plus half rho. So this was your differential form, or just a conservation of energy. We will also look upon Bernoulli's equation, but in some another approach, or you can say integral way. But basically both means the same. We'll also look upon the Bosniak approximation, that we told that it is nothing but in some way it is also closely related to continuity equation. And we'll also see several boundary conditions that a fluid flow would associate. Okay, and then after finishing this chapter, we will be in a shape to work on real fluid scenarios, and we can actually seek the solution of Navier-Stokes equation on real problems after finishing this chapter. Okay, and that would be our next chapter. So as an introduction, all fluid mechanics is based on conservation laws, that is mass, conservation of mass, conservation of momentum, which includes linear and angular. Both are important. And lastly, the energy conservation as well. If at all you are looking in the energy perspective, such as you are looking at the heat transfer across the boundaries. If you are not looking at heat transfers across body, then mass and momentum is enough to see the behavior of fluid flow in certain scenario. Okay, these laws, conservation laws, can be stated in differential form and integral form both. So differential form we have already seen. It was in the form of some dou u by dou x plus dou v by dou y, or in short dou u I by dou xi in tensor notations. So this was essentially a differential form of continuity equation. We'll see differential form of momentum equation as well. But in this chapter, and this differential form was applicable at a point actually. Okay, this was the key point that I wanted to notify. The differential form are related to a point only, or what we do, we will take an infinitesimal point as a cube, and we do the analysis, and we will see whatever the, let's suppose this is your dx, this is your dy. So on this element you are looking at conservation laws, and then you come up with this particular thing in differential form. Okay. But in this chapter we will look upon another possible way of looking at things, and that is the integral form, and which is applicable to the extended region. So extended region means fluid particles are not only a single infinitesimal thing, but it encloses the whole volume. Okay, so when this thing is being integrated over a whole volume, or we are looking at in the perspective of the whole scenario, then what we should go for is integral form of any conservation law, whether it could be mass or momentum. So this particular chapter will be focused on the integral form of, so working with integral form will be the essential ingredient for this chapter. To understand the integral form, the usual integral forms that we are going to come across is the time derivative of any integral. Okay, so any integral which is associated with the time derivative or some derivative, usually we will come across with this kind of forms, and so we have to tackle this integration in particular way. I mean, we need to solve it, obviously, so we need to simplify it. So while simplifying, we will take help of something called Leibniz theorem. Okay, and we generally will come across in this particular chapter the time derivatives of volume integrals. We generally do. I mean, once I understand this, I will be able to um, do my uh, uh, mm, solve or derive mass conservation, momentum conservation, and everything, because these conservation equations often needs time derivatives of volume integrals. Okay, so this is your usual uh, time derivative of any field. So this f could be scalar, vector, tensor, or anything. Okay, and this would be in field x, y, z, t. Okay, in general, and this could be scalar, vector, or tensor, higher order tensor, could be anything. And usually we want things to be uh, changing. I mean, basically this is nothing but the change of this integral, volume integral of this vector field or of this field with time. Okay, so before going into the actual form of Leibniz formula, uh, let me go through uh, the simple case first. So the simple case is what we actually need the derivative of, let's suppose I want to go from A to B. So simple form means, I'll take one dimensional case. Okay, and also where your function is I mean, function limits are, so usually what you could expect is v will be a function of t, or your x will be a function of t. T is here, but it will be a bit complicated. But let me start with this as a constant, and let's move ahead step by step. So first we'll take these constants and then try to solve this, what this expression come out to be, and then we'll take as time dependent limits, and then we'll try to solve that, and then we will connect this with our mass conservation in real scenario. Okay, once we understand this, so let's suppose I want to uh, I have the function which is function of x comma t, and this is x, and these are constant. Your constants are not changing. Okay, and you want to simplify this. So what is this actually? In if I have to plot fx, I mean, what exactly is this? Let me show you. So this is your f, this is your let's suppose one dimension I'm taking x only, so dx is there, only x is there. So you have a sum function fxt, fxy comma t. You have some function, it is going something like this, my fx comma t, and you want to see the rate change of this function, not this function, basically the area of this function, right? This is your area under this curve. So basically from A to B, you are looking from A to B. So this is your first area at initial time at t is equal to 0. So this is at t is equal to some initial time t1, let's suppose. After time t2, your function value, since this is function of time as well, okay, so this function may go somewhere else. I don't know, I mean, it may move into space. But the catch, I mean, the simplicity here is you are again looking at things at same interval. Okay, so at A only and at B only you are looking, and now you see uh, the area under the curve. So area under the curve would be the whole thing. Okay, so rate of change of with respect to time is equal to, basically I can write in this fashion. So any differential. So let's suppose dA by dt. How do you write dA by dt? So you write limit delta t tends to 0. Okay, a, so I'm going forward in time minus a at that time divided by delta t. This is how we write, right? In similar fashion, I want to write this. So what I'm going to write this particular integral as, so d by dt of this function ab fxt dx. So this is your whole function. I want to write is in this form, limit delta t tends to 0. Okay, and I want to advance in time, and I want to seek the advancement in time because I'm taking the time derivative, and the real, so the function at advanced time, the function at previous time divided by delta time. Okay, so function at advanced time would be what? So a to b, so these are constant, nothing to change. Fx comma t plus delta t dx. Okay, minus a to b f x comma t dx. Okay, divided by what is your delta t, right? Now I write this function, this advanced, I mean one step ahead. So this was your fx comma t plus delta t. Your function maybe have advanced in time and looking something like this. So this function can be written as can be written as in the form of Taylor expansion. Okay, that is associated with the previous function, right? Generally we do that. How Taylor series expansion we do? So this particular function in advanced in time is written as fx plus, so, or you can write fx comma t plus dou f by dou t. Time has advancement because I'm looking in the time derivative sense. Okay, so time t into delta t plus higher order terms, I can tell dot to f by dot t square times delta t square and so on. Since delta t will be smaller, then we can neglect this term and we can take this term over here, and let me write that. So this I can write fx comma t, and this is your plus dot f by dot t times dt and whole dx a to b minus a to b fx comma t dx divided by dt. So you can see these two things can cancel out each other, right? So these have same limits, right? Same limits. So this thing and this thing could be cancelled out. So we are left with limit delta t to 0, and you can see dt over here, dt over here. Okay, and yes, so what I can explicitly tell that, so limit will go away because delta t will not be there. So the only thing is left with a to b. So just notice what happened here. Dou by dot t f, okay, and times dx. See, beauty, what is the beauty? So you started with dy, or since there are no other derivatives, I can write d by dt. So I started with d by dt, the derivative outside, and it has gone inside actually. So d by dt has been put inside. Basically this is your a to b df x comma t by dt. Okay, the derivative went inside times dx. That's all. Okay, so this is very straightforward. It means if my time derivative would not be here, I can actually write this integral as df by dt dv. Simply, if this would be a constant, if the volume of your surface, I mean if your control volume is the volume of control volume is not at all changing with time. But usually it doesn't happen with fluids. Usually we have all sorts of deformation of your control volume, and everything happens, volume changes. But in simplistic sense, we can actually arrive if my v would not be a function of time, or v was not varying with time. Okay, so this is straightforward. Okay, now let us take a complicated case where a and b's are a function of time now, and then I will relate everything with our mass conservation, how we are going to look at into the mass conservation as a whole. Okay, let me do that. So this time let me draw uh, let me draw the function in this way. Let's suppose I have d by dt. Okay, I want to take the integral a t bt. The reason being, I don't want to derive all this Leibniz theorem, but actually this is the key ingredient towards advanced fluid mechanics to understand all, because all my equations will be based upon this. So I thought I could do the emphasis on this particular equation to derive it. Okay, and this will be invertiges also, x comma t dt. Now a bit things bit complicated when your limits are also changing with time. So advancement of your function is also happening along with your limits are also advancing with time, or as a function of time. So now if you plot your function and your, let's suppose one dimensional case I am taking, this is your initial function. So this is your f x comma t, this was your a, this was your b. Now function might have moved, I don't know, somewhere here. So this function is f x comma t plus delta t, but the problem is a also has moved, okay, slightly. So this is your a plus delta a, and this distance is delta a distance, and b also moved slight distance, I don't know, somewhere b plus delta b, and this distance is delta b also. Now I want to evaluate the change. Okay, so change could be what? So initially you have this much area till here only. Now you have this area as a whole. So you can see that you have, and you want to seek the change, so you have to take care of actually this area you have to take care additionally. Okay, and rest I mean rest of the area, it could be infinitesimal, and we can think of is at a previous case, but the thing is this area and this area you have to take care extra. Okay, now let me do the derivation, slight derivation, and let me okay, so let me do the derivation here. Let me change the pen. So now I want to write the things in limit form again. So limit form कैसे हम लिखे थे? We will see it, do it again. So final time step पे, so this is a plus so basically this is delta a is I mean to be more precise, this should be written dA, I mean a plus dou a by dou t times dt, isn't it? This would be b plus delta b by dt. Even b might be a function of time, that is why I am telling, and jitna time step aap badhaye, so that would be the actual value here, right? So a plus, and essentially this is the increment is delta a only, right? Because dt goes, but this is the way we should write. I mean, function at some value, function at a neighboring value. So a plus dou a by dou t times dt. This is the advancement, b plus dou b by dou t times dt. Okay, and the advanced function t plus delta t dx minus of previous one, right? So what is my previous one? Fx comma t dx. Previous one is a to b and divided by delta t, and limit delta t tends to 0. So this is your integral. You could write this integral as this form, right? Okay, so what I will do, I will okay, we can do the all sorts of manipulation, but what my idea is, if you do it properly, if you have to add some terms and you have to subtract some term here, plus I minus I, where I would be some function of fxt, you go under this uh, proper rigorous algebra. You will come and you will see that not only this, the time derivative is absorbed inside, but you have an additional two terms that uh, you will be looking at here. These terms are basically associated with these areas what we have uh, told, looked upon. So the final form, let me write the final form, because uh, obviously, I mean, this is of no use going into rigorous algebra, but yes, you can actually show that if you do it properly, you will get something like this. Let me write that. So this d by dt of at bt f x comma t d t x in one dimensional sense is equal to a to b or at to bt dou f by dou t times dx. So first term was intact. I mean, this term was there all the time sitting. I mean, you can say the usual integral. If it would be without uh, temperature, sorry, time functions, their limits would not be a time function, then I could write this plus additional two terms. I'll get dv by dt function value at b comma t minus dA by dt function value of a comma t. So these two additional terms are actually nothing but the area, these areas you could see. So this is your function height times this, so usually associated with this, this, and this is associated with this, and one you can see one thing is plus and one thing is minus. So in some sense, this area is, in some sense, it is coming into the picture and it is going out of the picture. So to take it as, I mean, sign convention, in that way you will get some, I mean, this area is plus, this area is minus to take. So basically this formula is a very strong formula, and this is called Leibniz integral rule or uh, formula. Now we will move one step ahead. Okay, so this was my one-dimensional thing. So dx was there, sitting over there, and this thing is something that is associated with the flux. That is, something is coming in, something is coming, going out, sort of thing. Okay, this thing, two things will take up. So this dx, one-dimensional thing, I will convert it to the volume as a whole thing, and this I will convert into some integral form. We'll see here. So as in a generic sense, that Leibniz formula can be now be written if your function, this x could be x comma y comma z, the whole thing, this v, your volume is changing with time. Now you want to see the volume integral of this function, and basically the time rate change of the volume integral can be written as the first equation has absorbed this dt term plus some of those influx and outflux terms that you should think in this way. Okay, it will be more clear once we derive the mass conservation now, and we'll come back this how this has come, because once you understand this mass conservation, you will again will be understandable easily where this terms has come. But this is sure that these terms come from this some outflow and some inflow of these integrals, right? So let me go through the conservation of mass through integral form. Okay, so conservation of mass is what basically?
That, sir, mass remains constant.
Mass remains constant. So let's suppose I have dm mass. Initially I have a dm mass. Let's suppose small particle I am taking, one small infinitesimal, and that mass is dm. Okay, and so I okay, wait 1 second. So what, so basically rate of change I am looking at. So what I'll tell that d by dt integral of this dm over integrated over whole volume, this is conserved quantity. Okay, so this quantity is conserved, right? D. So essentially this is what, this is m dot, nothing more than that. But this is written in this fashion that dm mass will take integrated over whole control volume, so the whole mass will be not changing with time. Okay, so this thing, so mass can be written as, can I write the mass with, so d is equal to m by v, so mass is equal to, mass can I write rho dv, can I write that? So I can write that d by dt rho dv integrated over whole control volume, this I can write. Okay, now you see it has been started. Whatever I've learned, it could be started now. Why? Now you have to integrate, I mean you have to do this volume integral, the right I mean the rate of change of this volume integral with time you need to integrate now. So this has been started. What we have learned just now, we have to put it here. So let's suppose I have a boundary volume v, capital V, okay, in which total mass was rho dv, and I want to seek what is my mass that is changing with time. So I will want to take the time derivative of this particular integral. So that is what I have done. Okay, so let's suppose for the simplicity of this case, let's suppose this boundary of volume is not changing with time. Okay, so not changing with time, remember, so vt is not a function of time, so vt is just v, it will be fixed. Now what I will write, integral, I mean dt will be come inside, this will be dou rho by dot t times dv. Can I write that what we have learned by using Leibniz theorem? Okay, now so rate of change of this mass is fine. This is the content mass, but something may go across also, right? We can think of m dot again by this formula, rho av. Do you remember? If at all your mass flux is cutting across the edge of the boundaries, it is going across the boundary. Okay, so this thing can be written as integral of this thing can be written as integral of rho u dot dA. So u is the velocity or rho v. So we will not tell because v and v will confuse volume, and so we will write u, right? And this is your vector dot dA vector. So whatever mass that flux that is cutting across the surfaces, any surface, either it is going out or it is coming in, that also contribute my change in mass, right? So that we have to account, whichever mass is going out or coming in, that we have to take account. Obviously the change of mass as a whole content we have taken care, but whatever mass that is going out or in, we also have to take care, and that will be defined by this flux. Okay, rho u, I mean rho times u times dA. So if essentially if you do the dimensional analysis, you will see that this is nothing but m dot. Okay, okay, now this thing, now we can relate these two. Whatever change in mass that is happening, this is because of inflow or outflow. Okay, so we actually these two quantities are same, so I can write that dou rho by dou t dv is equal to rho u dot dA. Okay, because the volume of flux is fixed, that is why we have put it sign here. Okay, so now what we'll do is, so rate of mass flow out of the volume is the surface integral, this. So we have related this. So the law of conservation of mass states the rate of increase of mass inside a container or a beaker within the fixed volume must be equal to the rate of inflow or outflow. We have to take care of, I mean this sign would be right now it is not, it is mundane, don't worry about this sign, but this will be the thing, I mean rate of change of mass must be equal to the inflow and outflow that is associated with it. Okay, that's for sure. Whatever tank you have, you are going to fill it, otherwise mass is zero initially and you are filling it. So whatever mass flow you are filling it, this will be the increase of dm by dt. So this is what it is written, this is dm by dt is nothing but what is the m dot that is coming in minus m dot, let's suppose this is having some hole, so m dot out is coming out, so m dot out is minus, would be minus sign. So change in mass with time in a control volume with a fixed control volume must be equal to the m in minus m out in rate form. So this is nothing, in integral form we have written. Okay, now we will also use something we have studied, that is divergence theorem. Okay, so what we have seen so far, this is dou rho by dou t dv is equal to rho u dot dA, and this is integrated over area. So now this thing can be converted to what would happen. Okay, fine, it to bend dou rho by dou t dv is equal to surface integral rho u dot dA. Okay, and this can be written as, you remember your Gauss divergence theorem? So you are going to relate your surface integral with some volume integral. In what fashion? So this is your this whole thing is your, I mean, the quantity you are looking at. This is the vector field or tensor field. So del dot rho u dv. Remember, you are going to change your surface integral to volume integral in this fashion. Remember, your any vector a dot or any f dot dA, divergence of f dv. Do you remember? We do that often. Now we are in some shape. So what, now this thing is equal to this, and you have dv things. Okay, now you can actually integrate things in a common platform. So I mean, right now you don't I mean, you cannot evaluate things, you cannot subtract it, but now you can subtract it since you have dv term here, dv here also. So get back in the left side. So dou rho by dot t minus del dot rho u, okay, and the whole dv. So this is your integrated over wall volume is equal to 0. Okay, so this is this form. So in any integral, let's suppose I have any integral, I have doing dx is equal to 0. Okay, and this integral, this could be 0 only when the integral of this, I mean, area under this function, area under this function is 0 only when this at each point, that only when I integrand is 0, inside integrand is 0. So that is why it we can actually tell that the inside integrand will be 0, and this gives rise to our continuity equation. Okay, and this is your, basically this is your integral form of mass conservation. And we can apply that this is your integrand inside integrand, this is also 0, and this is actually the continuity equation that we can think of. We can do some sort of manipulation, likewise this particular uh, identity can be actually think of. So this is what, so this is del dot rho u. So we can actually think of in tensor notation. So this is what, dou by dou x I. So this is what, rho u I, right? This is this thing, and this can be written as, so one time your rho will be outside, dou u I by dou x I, and one time your u will be outside, and dou rho by dou xi I should write. And what are these actually? These things are repeated index, so you have a summation sign over here, you repeated, you have a summation sign over here, you have summation sign over here. Okay, but you can write in this fashion. Now you can actually write dou rho by dot t plus, you have to take this one, so you can write this term first, ui dou rho by dou xi. Okay, plus this term you should write rho dou ui by dou xi is equal to 0, and these two terms collectively, do you remember the total derivative we have come across in our Lagrangian description, total derivative? So this will be written as so I will also do one thing, I will divide it by rho everywhere as a whole, and this can be written as d by d rho by d capital dt 1 upon rho plus, this is what, this is your usual del dot u, isn't it? is equal to 0. So this is the rate change of density following a fluid particle. Basically, this is the Lagrangian description derivative of d rho basically. So yes, the continuity, the generic continuity equation boils down to 1 by rho capital D rho by capital dt plus the divergence of velocity field must be equal to 0. So this is also called continuity equation, but very generic continuity equation, you can say. And yes, next is to derive your linear momentum equation. Linear momentum will look upon, okay, and there we will have to take care of. So far we have not come across this term, but there it will come, that when your volume is not fixed with time, I mean things will be more complicated there, and we'll see there. So far so good. We will not go now. Okay, any doubt?
No, sir.
Okay, fine. Okay, then I can take the attendance, and